Welcome to the workshop. Today we want to take a look at section 4.5, Directed Graphs and Multigraphs. What we're going to do for this section, like the last two sections, is we're going to present the definitions and theorems in this video right here, and then there are a collection of videos for each of the examples. So it's a little bit different than what we've experienced for most of the course so far, but this I think works out pretty efficiently, and it's a little bit different. The examples are on the chalkboard, which is a little bit more fun. At least I think so. So let's take a look at our definitions and theorems for directed graphs and multigraphs. All right, so a quick note, if you are uncomfortable with, let's see here, basic definitions, breadth first search algorithm, or what Euler circuits and paths are. If you're uncomfortable with any of these three things, I would first encourage you to go back and look over those things again, because this section is referring to those things quite extensively. Okay, so we want to make sure that we know those. And you should be reading the textbook, and you'll find that when you do that, there are some things that we're not talking about. So if it's completely ignored in the videos, then usually we're not going to be talking about it, and it won't come up in the homework. But you should at least skim over those things. If they don't appear in the homework, if they don't appear in the video, hey, thumbs up. A little bit easier for you. All right, so let's take a look at our first definition. All right, a directed graph is, right, it's essentially a graph, but what we're doing is we're assigning a direction to each edge. So directed graph is a finite non-empty set V, again, that's still the vertices, and a set E, that's still the edges. But what's different here is that the edges are ordered pairs. So now instead of just being a two-element subset of the vertices, they are ordered pairs of distinct elements from the vertices. So we're not using loops here. And in fact, we also do not want to have any parallel edges for the most part. Although I do think that it is in some ways acceptable as long as they're pointing opposite directions. So we'll see what that looks like pretty quickly here. So again, the elements of V are still called the vertices. And the elements of E are called, instead of just edges, they're called the directed edges. So that's nothing too crazy so far. Now, when we look at a specific edge, right, it's an ordered pair, A comma B. So this is the directed edge from A to B. So if we have vertex A and we have vertex B, we no longer have just a straight line, we have a directed line. It has an arrow at the end, okay? So arrow from A to B. All right, now we also handle the degrees a little bit differently. The number of edges from A, so if we have a vertex A, the number of edges from A, extending from A to somewhere else, is called the out degree of A. So 3 in this case. And the number of edges that are coming into A from some other vertex to A is called the in degree of A. And in this case, it'd be 2, right? There's 3 edges going out from A and 2 edges coming into A. So out degree 3, in degree 2. Excellent. So this is still just a graph that looks a little bit different. What do these graphs look like? Well, here's an example of one, okay? All of our edges now just have arrows on the end. So when I travel this edge, I can only travel it from this vertex to that one. I believe these should be labeled A, B, C, D, and E. So I can travel from C to B, but I cannot travel from B to C. C to B, yes. B to C, no. Okay, because the arrow goes from C to B. So that's the idea of a directed graph. Here's a really basic example of one. All right, again, this example will be completed in another video. So let's look at our definition. So we're just taking directed graphs, right? We took a graph, we added a little bit, gave direction to the edges, and here we're going to continue expanding on the things that we're already familiar with for a graph. So let's see here. There we go. An alternating sequence of vertices and directed edges, right? An alternating sequence of vertices and edges is a path. Here, where we have an alternating sequence of vertices and directed edges, we have a directed path. Okay. And it's a directed path from V1, of course, to Vn plus 1. And much like the edge E had to connect the two vertices that it's next to, in this case, it does specifically have to connect, let's see here, EI would have to connect VI to VI plus 1. I do believe that is, right? V2, E2, V3 would be next. So E2 connects V2 to V3. EI connects VI to VI plus 1. Yep, excellent. So beyond that, the length of a directed path is still n. The length of this directed path is n, right? It's still just the number of edges that we travel. So nothing has changed there in terms of the length of a path, but the path itself has changed. I can't travel any direction I want. That direction has to be specifically the direction of the arrow. So a directed path with no vertex, let's see here, repeated, is called a simple directed path. So still the same thing. A simple path does not repeat any vertices. A simple directed path does not repeat any vertices. Nothing new there, just new context. All right, so a directed path from vertex A to vertex A, right? So if my initial and terminal vertices are the same with no other vertices repeated, previously that was a cycle, and still it is called a cycle. In this case, we're just traveling in the direction of the arrows. All right, and this is something new. And previously, we said that a graph was connected if we could travel from one vertex to another along a path. As long as between any two vertices, we can travel from one to the other, then it's connected. Here, if we have a directed graph with a directed path from A to B for every ordered pair of vertices, A and B, this is called strongly connected. So it's really important to recognize that this graph right here, for example, would not be strongly connected because I can travel from A to B, but I cannot travel from B to A. So while this, right, I can get from A to B, so isn't it connected? We give it a different name. It's not strongly connected because we cannot get from B to A. Okay, so it's strongly connected when we can get from A to B and B to A. So we would have to add this edge here as well. And this is still a directed graph. There's no problem because the ordered pair AB, which is this vertex, is different from the ordered pair BA. Those are two different things. All right, and frequently what we can do is we can actually, rather than giving two separate lines, if we wanted to, we could give one line with arrowheads on both ends, and that would be acceptable. All right, so again, the example that follows is given in another video that will follow this one. Same thing with this example, and that brings us to Euler circuits and paths. So we'll just finish up with our last definition and theorem, and then the following videos will cover all of the examples. All right, a directed path and a directed graph that includes exactly once all of the edges of the graph and has different initial and terminal vertices is called a directed Euler path. So that's hardly different from what we have seen previously. a path that contains all of the edges is called an Euler path. That's still what we're looking at here. We're just looking at it in the context of a directed graph. So the path would have to be a directed path. All right. Of course, if the initial and terminal vertices are the same, the path now becomes a circuit. So it's called an Euler circuit. Excellent. All right. So how can we be certain that there is or is not an Euler circuit? All right. So we said previously that for a graph, for a multigraph, if we have that the degree of each vertex is even, then we do in fact have an Euler circuit. We change that slightly here. For this, it still has to be even overall, but it works out to be that we have to have the same in degree as out degree. So if the in degree and out degree are the same for every vertex in a directed graph, whose underlying graph, of course, is connected. It doesn't, so the graph overall does not have to be strongly connected, but without directions, the graph needs to be at least connected. And then with the directions, the in degree and out degree must be equal. When we have that, it will in fact have an Euler circuit, a directed Euler circuit. Okay, and that's what the last example will highlight. We'll find an Euler circuit for this. So there is, we have an algorithm, the Euler circuit algorithm. We just adapt it slightly for the directed graph. So the adaptions are pretty simple and straightforward, and that will be included in the discussion in the example. All right, so that's all that I have for this introduction of definitions and theorems. So we'll continue on with all of the examples in the coming videos. So I'll see you guys back here in the workshop very shortly.